around. Okay, as a byproduct of this construction, I have like some other properties that I would like to mention. So the first one is like the law of this process theta t. So you remember, originally theta t was a Brownian motion, but then I changed the probability space, so it's not a Brownian motion anymore. But it turns out that I can describe its law very explicitly. So theta t has the same law as Tx plus wt where, okay, so recall W was a standard BM. And X is a random vector having low mu, independent of W. So why is that so? Yeah, under Q. So now everything is under Q. So yeah, there's no Q anymore. Because, yeah, but I mean, I will not change. I have changed the measure once and for all, and then there's no coming back. Yeah, okay, so this I should have commented on this. So let's say, okay, maybe let me make a short comment on this. So for my purposes, it's enough to define the process on some finite fixed time horizon. So if you want, it's like I have a finite time horizon. So I could eventually let t tend to infinity and argue that by some abstract argument, the process, I can define it on R+, but I don't need that, so I don't want to bother you with this. Okay, so from our construction, okay, maybe I said there is no coming back, but maybe just a last coming back. So theta was some Brownian motion, and then I changed the measure. Okay, so so the expectation. So if h is some test function of the whole trajectory, so maybe like okay, let me for the last time mention Q and P. So from our construction, this was the expectation with respect to P, and then I changed the measure. So my change of measure was something that I call dt, and this thing here was dt, you had some expression of the form x of some function which I call theta t and theta t. Okay? So if I want to like emphasize like this new Brownian motion, so this is h of w, because under P theta was a Brownian motion. Wt. In other words, theta, so the process theta t, its law is absolutely continuous with respect to that of the Brownian motion. With respect to Brownian motion with density phi, well, maybe this is not, I mean, the function that maps W to phi of t is wt. Okay, so this is somehow given by my construction. So all I need to show to you is that this also has the same density. Okay. Now, if I take expectation, ah oui, pardon. Merci. Now if I let eta t be let's compute expectation, like take the same test function. So let's first condition on x. Okay. Okay, when you condition on x, Wt is just, so this process is just a Brownian motion plus some constant speed drift. So for this, you have an explicit formula for the density. It's pretty easy. So condition. So let me maybe condition on. Then what you will get is that so this is h of w, and then you have to take that into account, and this is x. X dot wt minus capital T x squared over 2. Okay, so this formula for the law of a Brownian motion plus some deterministic drift, it's called the Cameron-Martin formula. Cameron-Martin. But actually here it's kind of it's a bit stupid to call it Cameron-Martin because my drift so Cameron-Martin is where you are allowed to put anything here that's deterministic and say h1 or whatever. Here it's something that's like a constant speed, so it's a baby version of Cameron-Martin. So you have I mean this sort of I mean you have more pedestrian ways to see this. Okay. Okay, so this means that the conditional this conditional expectation is this, and now you take expectation again. Okay, so it's expectation of this expression. But then I know that capital X and W are independent. Okay, and so I will use Fubini. I will so here I did first the expectation with respect to W and then to X, and then I do the other way around. Okay, so this is expectation H of W. And if you want, I put the expectation on X inside this big expectation. Okay? So X has low mu. This is integral X of Wt minus T over 2 X squared d mu. Okay? I just put the expectation with respect to X inside this big expectation. And W doesn't depend on X. But that's precisely the definition of capital phi. Okay, by the way, this is formula for the law of like this theta t. So it was somewhere around, but the first explicit mention of this law, the first computation, done a bit differently, is in the Klartag-Puterman paper that I mentioned. Alors ça, je ne sais pas si je le fais ou pas. Okay, maybe I skip this comment. Okay, so now there's another thing that I want to tell you about is time reversal. Okay, so it turns out that the description of all this becomes a lot more simple if you just reverse time. Okay, so why? Okay, so observe that mu t of dx okay, if you have a test function, so integral f mu t of dx, okay, so it's integral f of x theta t minus 2x squared mu of dx, and then I divide by integral x. Okay, so maybe let me introduce rho of x equals d mu over dx. Okay, so this is integral f of x blah 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 rho of x dx divided by integral x blah rho of x dx. So this expression here, after all, is just the convolution of f times rho by some Gaussian. Okay? So if you know the heat semigroup, the T should be downstairs. Okay? And here the T is upstairs. So maybe I should reverse time. So let Pt be the heat semigroup. Okay, so Pt of x. Okay, not confusing, so I will Ps. Ps of x. So expectation f of x plus ws, it's semigroup. Okay, so it's f convolved with gs at point x, where gs is whatever. Very good. Then integral f d mu t is okay. It's p1 over t f rho let me, so I want to like pull this t off here, so probably it's theta t over t. Okay, so far I did nothing. Okay. Okay, observe also. So theta t no is the same as tx plus wt. So theta t over t, same you know, as x plus wt divided by t. Okay, I promise time reversal. Okay, set S equals 1 over t. Okay? Okay, so integral on Rn f d mu t is this, but I replace all the 1 over t's by S. Alors là, la probabilité que je ne me plante pas avant la fin. Moreover, okay, theta 1 over s times s, so in law, is the same as x plus this, but I replace t by 1 over s, okay? So SW 1 over S. Okay? And now, Bernard?
Yes.
Okay, this is this is again a Bourgain motion in S. This is time reversal property of Bourgain motion. If Bs is a Bourgain motion, S times B1 over S is also a Bourgain motion. Okay, so far so good. Okay, so in law, integral Rn f d mu t. This is the same as, let me give a name, QS, right? I will use this notation, possibly. No, it's QS of F, sorry. F is BS. Where QS F at point X is okay. Moreover, you can interpret QS as sort of the adjoint of PS. If you look at this in the correct probability space, so this I always get it wrong, but let me try, and then maybe I'll. So I got it wrong. This is simply because all I'm saying is that if you do integral QSF G d mu equal gamma s. This is integral. No, I'm confused. Yes, mu equal gamma s as density ps rho with respect to the Lehec measure. Yes. Yeah, sorry. Yeah, I'm very slow, sorry. Yeah, this was a long line for something that's supposed to be simple, but okay. Maybe if you rewrite this with expectation, it will be, this is the same as writing expectation QSF so here I'm integrating with respect to mu equal gamma s, so it's x plus vs g of x plus vs equals here integral, so expectation f of x. Okay, I sort of lost track, so where I want to go here. But, okay, let me go on. Maybe I'll end up where I want anyway. PSG at x. Qu'est-ce que j'ai envie? Pourquoi j'ai fait ça? Ah. Yes, so PS of G is expected at point x is expectation of G at x plus BS. So for every G. Okay, so this means that the conditional expectation of f of x condition on this vector is okay, the conditional, so whenever I hit this guy against someone that is that depend on this variable, I obtain this. So by definition of conditional expectation, this means that this variable is so at the end of the day, okay, so summary. So in law, integral f d mu t is the same as the expectation of f of x condition of, okay, where here there is the convention that t is 1 over s, okay? Yeah, okay. So here there's some stuff that on which I'll stay a bit quiet. Yeah, okay. Okay, so when I constructed the process, I had to stop at some time, capital T. So here S is only from 1 over capital T to infinity. But of course, this makes sense when S tends to 0 also. So okay, let's be vague about this. So at the end of the day, stochastic localization. So maybe I don't write, I just say it. The stochastic localization process is you start with a random vector x which has law mu. Then you look at the conditional law of x, condition of some noisy version of x, plus some, you add some Bourgain motion. You look at this as a process like that depends on all s, and then you reverse time. And that's stochastic localization. Okay, so this is like a much simpler description. So you could say, but why did you bother us with all the rest? The thing is that when you, the good thing is of reversing time and writing this way is that you can compute derivatives. I mean there are things that I know how to prove about this object by reversing time. I don't know how. I have no idea how to do it directly with this. Okay, so maybe Boaz will tell you tomorrow that he thinks that this should be amenable to like functional analysis method, and that it should be possible in principle to remove all stochastic arguments. But so far, this has been we have not been successful in doing this. I mean, we still don't know how to avoid this use of stochastic method. So in that formula, when t goes to 0, you see it's like t or s goes to 0. Ah, okay. So when t goes to 0, the measure mu should be, so when t goes to 0, mu t goes to mu, t goes to 0. Okay, you remember mu t was perturbed by something like when t is very small, it's like the perturbation is very small, okay, because it's so this means that when s tends to infinity, this should be very close to the law of x. But this is clear. I mean, if you start with a Bourgain motion, and then you perturb, but if s goes to infinity, your perturbation like is macroscopic. I mean, it's you have no information whatsoever. If s is very, very large, and you only know x plus bs, so some noise whose variance is s, but if s tends to infinity, you know nothing. I mean, you just see the noise.
So x becomes independent of x plus bs.
Yes, if you want. Yes. In the limit.
So this is essentially expectation of f of capital.
Yeah. This is. I mean, this tends to expectation f of x. When s tends to infinity, yes. Okay. Maybe one last comment. So recall mu was, so my mu t of dx, okay, so it was mu of dx times some Gaussian perturbation, x of theta t minus t squared t divided by integral r. And theta t has the same law as tx plus wt. So you could argue, but why did you bother us with Girsanov and such? And why don't we just define mu t of dx equals mu of dx times x tx plus wt minus tx squared over 2 divided by what you should divide. Okay, in other words, why didn't I take this as a definition of theta t and run the same thing? It has the same law. This doesn't work for the following reason. Okay, so this doesn't work. In the sense that this has the same law as the contraction I gave you. So if it has the same law, this means that this mu t is a martingale with respect, so it's a martingale because it has the same law as the other thing that has a martingale, but it's a martingale with respect to its own filtration, okay? And it is not, in general, a martingale with respect to Wt. But not with respect to that of Wt. Okay, this kind of bogus thing happens quite often in stochastic calculus. So maybe just to wrap up, I give you an example where you can compute everything. I won't do the computation. So in 1D, take mu to be a gamma Gaussian. So in this case, you can compute everything. So this function phi, you have an explicit expression. So the equation for theta if you start with the original construction that I give is d theta t equals okay, I just give you, so you'll get theta t equals 1 plus t times integral dws over 1 plus s. And for instance, the equation for at you will get, so which is the barycenter, you will get indeed a martingale. And if you start with, if you, I don't know, put eta t equals tx plus wt, so I can give you it as an exercise. So the exercise is, so take a Brownian motion, take this theta t, and this is at, and then here, okay, maybe this is the other theta t, so theta tilde if you want. And so the a tilde, which is theta t tilde over 1 plus t, so it's tx plus wt. So now the exercise is here. The exercise is that show that, so directly in that case, so it follows from the theorem that I told you, but here you can show directly that theta t has the same law as theta tilde t. Hence, at has the same law as at tilde t. But at tilde t is not a martingale for W. Okay, so on this example, you see that somehow having this identity law is not enough to be able to do the computation that I want to do later on. So if I start with, if I take this to define the stochastic localization as a definition, then it won't work. I won't be able to apply Ito's calculus because then the formula won't match. So this is a subtlety that I wanted to tell you. But if you didn't like it, you can ignore this. I mean, I won't use it. Sorry, this is, I think, enough for today.